Hello engineers, welcome to the new video of the course, and in this particular video we are going to focus upon the different types of semiconductors, and specifically in this particular section we are going to deal with intrinsic semiconductors. Okay, so let's start this session. And when we talk about semiconductors, so basically we are talk about the two different types of semiconductor. The very first type is intrinsic semiconductor and the second type is extrinsic semiconductor. Okay, so as I had already mentioned that we are going to focus, in this particular section we are specifically going to focus upon the intrinsic semiconductor. But before that, let me just give you a rough idea like what exactly is the difference between extrinsic and intrinsic. So when I talk about intrinsic, okay, when I talk about intrinsic semiconductor, intrinsic semiconductor, so that means I'm talking about purity. Okay, just remember these two words whenever we are dealing with intrinsic semiconductor. So basically we are dealing with pure atom, and whenever we are dealing with extrinsic semiconductor, extrinsic semiconductor, so basically we are dealing with impurity or impure atom or impurity. Okay, I know most of you guys might have this particular question that what exactly is this, what is pure and impurity. Okay, so basically let's assume you have a semiconductor. You have a semiconductor, okay, semiconductor which is made up of, suppose, X atom, okay, which is made up of X atom. So that particular semiconductor, it is known as intrinsic semiconductor. Okay, whereas let's suppose if you have certain semiconductor, in which I'm actually mixing two different atom, or rather let's suppose you have one semiconductor X, and in that you are actually adding another another atom. Okay, so this particular semiconductor or this particular type, it is known as extrinsic semiconductor. So basically what we are doing, we are actually adding certain Y atom in X atom, right? So basically we are actually enhancing its impurity, right? So this was pure atom, right? You try to understand it in this way. You have gold, 1 gram of gold, or maybe 1 kilo, generally we take it in gram only. So maybe let's suppose you have 10 gram of gold, okay, and let's suppose if you are adding 1 gram of maybe some other metal, okay, or 1 gram of impurity. So it's something like that only. Okay, I hope you are able to understand this. Okay, so extrinsic means what? You are actually adding certain Y atom. Let's suppose you have X atom of semiconductors, you are adding certain Y atoms in it, so that becomes the part of extrinsic semiconductor. On contrary, if you have a pure semiconductor, let's suppose if it is made up of X atom, so that is known as intrinsic semiconductor. Okay, so this is the simple definition between the intrinsic and extrinsic semiconductor. I believe that you are able to understand this particular concept. Okay, in if you type this definitions on Google or maybe on ChatGPT, you will get huge paragraph, and we don't know, we don't want to go in that detailed way. We'll just try to stick to the point and try to understand the concept, and then we will try to apply the same concept in the field of electronics. Okay, great. So now let's proceed further, and you can clearly see over here I had clearly mentioned that pure or without any impurity. Okay, intrinsic means what? Pure or without any impurity. Okay, that means the atom or the crystal, it is present in its pure form. Okay, great. Now when we talk about a semiconductor, so as I had already mentioned that we generally in today's world, we whatever the semiconductor devices you found, it is made up of silicon. Okay, and very few of them or negligible of those particular materials or the components, they are made up of germanium. But yeah, when we deal with extrinsic semiconductor, so basically there you would get lots of atoms in the impure form, right? So basically we fused two different semiconductors and all, so lots of things happen in case of extrinsic semiconductor. But since we are dealing with intrinsic semiconductor, so it is either made up of silicon or it is either made up of germanium. Okay, so now you just focus upon the atomic number of silicon. Okay, and now we will try to write its electronic configuration. So the electronic configuration for silicon is 1s2. I believe that you all guys know how to write the electronic configuration. 2s2, 2p6, then we have 3s2, alright, and then 3p2. Okay, 3p2. Okay, great. Now remember one thing, the atomic number for germanium is 32. I know most of the students who are not from chemistry or the chemical background or the chemistry background, they will ask me from where you are getting this particular number. So you just go into the periodic table and you just focus over here. See this particular number. So you see silicon and you see this 14. So 14 is its atomic number. Similarly, you see this germanium. So this is 32. That means 32 is its atomic number, right? So how we are going to represent its electronic configuration? It is quite simple. Let me just represent it. So 1s2, right? 2s2, 2p6. Now I won't explain each and everything because I had already explained you this particular part, right? How exactly we follow this process. 3s2, 3p6, 3d 10. Let me just calculate the number. So let me just add them all. So 10 plus 6 is 16 and 2 is 20. 16 and 2 is 18. 18 and 6 is 24. 25, 26, 27, 28. So 28. Okay. So 4s2, and then we have 4p 2, right? 2 to 4, 14. This is 20, 22. Then we have 28, 30 and 32. Okay, great. So this is how we actually write the electronic configuration for the germanium. Great. Now if you look over here, let me just erase this arrow, sorry, that tick mark. Okay, so you just focus upon this particular part. See, just try to understand this particular part. See, this is my N shell or the fourth shell, right? So this is my fourth or N shell. Okay, similarly if you look over here, this is my M shell or the third shell. So this is my third or M shell. Okay, so you see, in case of silicon there are 3 shells, okay, or the 3 orbits, whereas in case of germanium there are 4 shell or the 4 orbits, right? But the point to notice over here is this. See, just have a look over here in the third shell or in the outermost shell. So basically this is the outermost shell or the third shell of the silicon. So it is the outermost shell, right? And in the outermost shell of silicon we have 4 electrons, right? We have 4 electrons in the outermost shell of silicon. Similarly, if you look over here in the outermost shell of germanium, we have what? We have 4 electrons. That means what? See, since there are like the electrons present in the outermost shell for both of the atom are same, so therefore the properties of both of the atoms would also be similar, right? So that's why they both are semiconductor. Okay, on contrary, if you see the energy band gap or EG, or sorry, forbidden energy gap, just have a look over here. See, forbidden energy gap for silicon I had already mentioned, it was 1.1 electron volt, whereas in case of germanium it is 0.72 electron volt. And I had clearly mentioned that your forbidden energy gap should be in between 0 to 3 electron volts to be a part of semiconductor, and we can clearly see that it is 0.72 electron volts, so it can be easily a part of semiconductor, right? So these two points, it states that our germanium is also a semiconductor. Okay, great. I hope you are able to understand this. Okay, so now we will quickly read this particular point. So they belong to the carbon family. Why carbon? As you can clearly look over here, carbon is present over here. See, carbon is present over here, and below carbon you will get silicon, and below silicon you will get germanium. So that's why they belong to the carbon family. And this is what we had clearly seen over here. 4 valence electrons. Valence means last electrons, okay, or the electrons which are present in the last shell. So you can clearly see 4 electrons and 4 electrons in both of these particular atoms of silicon and germanium, or 4 electrons or valence electrons are involved in the covalent bond formation in Si or Ge crystal. Okay, and now this time I won't explain what exactly a covalent bond. It's quite simple, right? I hope you all guys have a basic idea about chemistry, and this is what I had clearly mentioned in the prerequisite of the course. But still, if you don't have any idea, let me just give you a short example to understand this particular part. Let's suppose you all guys are eating ice cream and I have a pastry or a cake, right? And let's suppose if I want your ice cream and if you want my cake, right? So basically what we will do, we'll share both of these items half and half, right? You will give half of your ice cream, I will give half of my pastry or cake, right? Okay, So basically this is what a covalent bond means. Okay, so if an atom has certain electron, let's suppose if there are two atoms, right? If let's suppose there are two atoms, atom A and atom B. If both of these atoms want to share their electrons, so that particular phenomena is known as covalent bonding. Okay, I hope you are able to understand this particular concept. Okay, if not, then I'm requesting you that you please Google this particular concept. Okay, I don't want to go behind this particular concept because I hope you all guys know me, right? If I go on explaining this particular part, then it might take more than 1 hour to explain me this particular concept, because in that detailed way I will explain you. But again, we our point of interest is going behind semiconductors, not behind the chemistry. So that's why I'm requesting you just you just get a basic understanding about this particular concept. That is also fine to understand the further concepts which are required to understand the intrinsic semiconductor. Okay, great. So now let's proceed further and let's read these particular points as they are mentioned over here. Okay, so you can clearly look over here. I had mentioned these 2 points. Let me change the color. Which color should I take? Maybe I'll go with this one or this one. Yeah. Okay, so you see, what we'll do, we'll just read this each and every point, and we will try to understand this particular scenario in detailed way. Okay, so you just look over here at absolute zero temperature. Now what is absolute zero temperature? So let me just write over here. Okay, absolute zero temperature. What is absolute zero temperature? That means we are dealing with 0 kelvins, or 0 kelvins can also be written as minus 273.15 degrees Celsius. So basically we are dealing with minus 273.15 degrees Celsius. This is what it means in this simple word. Okay, so at absolute zero temperature or 0 Kelvin or minus 270 degrees Celsius, there are no free electrons. Okay, as all the valence electrons are involved in the covalent bond, a semiconductor will behave like an insulator at absolute zero temperature. Okay, so long story short, let's suppose if I have a crystal of semiconductor. So this is my semiconductor crystal. So all of the electrons would be involved in the covalent bond in this particular crystal, and none of the electrons would be free. What does that means? Okay, so you just we will just proceed further. Okay, so again, if I consider a crystal of silicon, so there would be n number of silicon atoms, right? But what I had done, I had just taken this 9 to 10 atoms, or sorry 9 atoms which is present in front of you, and with this particular 9 atoms we are going to understand or analyze this particular concept. Okay, great. So as I had mentioned that these are 9 atoms of silicon. You can clearly see 1 2 3 4 5 6 7 8 9. Okay, now you just have a look over here. What we studied when we started this particular session, we studied that 4 electrons are present in the outermost shell of silicon and the germanium atom. Okay, 4 electrons are present in the outermost shell of the both of the atom, that is silicon and germanium, but you can take any one into account. Either you can go with silicon or else you can go with germanium. Okay, I will prefer to go with silicon because most of the components and most of the devices that we are using today, right, laptops, computers, your desktop, anything, smartphones and all, obviously semiconductor, or that basically ICs are used, right? So all of them or most of them, they are made up of silicons. Although extrinsic semiconductor are used, but silicon plays a very significant role in extrinsic semiconductor as well. So that's why I will prefer to go with silicon instead of going with germanium. But the overall concept remains the same in case of germanium crystal as well. Okay, so as what we saw that 4 electrons are present in the outermost shell of the silicon or the germanium atom. Okay, so you can clearly see, let's suppose if I'm dealing with this particular atom, silicon atom, so it has 1 2 3 and 4 electrons. What is this? So basically, as I mentioned that basically each and every silicon atom, they are trying to make a covalent bond with its surrounding silicon atom. Let me just write over here. What we can figure out from this particular image is, just a second, let me just write this particular point. Each and every silicon atom is making or is forming a covalent bond, a covalent bond with its surrounding, with its surrounding Si or atom, okay, because might be some of the students will go with germanium, some might go with silicon, so that's why I had written atom. I had not written specifically as Si or Ge atom. Okay, great. So now let's suppose if I'm taking this particular atom, so it has 1, 2, 3 and 4 electrons, right? And as I had mentioned the concept of covalent bond, that if you have certain thing, if I have certain things, right, and both of us, we want to share this particular atoms that we have, or sorry, this particular things that we have, right? So what we'll do, we'll do sharing, right? Similarly, if you look over here, this particular atom, it is sharing its electron with the surrounding atom. You just have a look over here, it is sharing its electron with the surrounding atom, and even the surrounding atom, it is sharing its own electron with the with this particular atom. I just forget to mention the electron over here. Yeah, you just have a look over here again. So this is my Si atom. It is sharing its 4 electrons with the surrounding atom. Let's suppose if I'm taking this this particular atom, so you see this atom also has 1, 2, 3 and 4. Okay, 4 electrons. If I take this particular atom, even this atom has 1, 2, 3 and 4 electrons, right? So you see the first electron of this particular Si atom and the second electron of this particular atom or silicon atom. So basically what they are doing, they are sharing their electrons. Okay, sharing their electrons, and basically this particular concept is known as covalent bond. Okay, so this particular concept, it is known as covalent bond. Okay, great. I hope you are able to understand whatever things that we had discussed till here. Okay, I hope you are able to actually like grasp this particular concept that we had studied till now. Okay, so now let me erase all of these things. And basically there are n number of atoms. I had just represented 9. So this particular electron which is present over here, that would also be sharing, or that would also be get shared with some other atom. Okay, let me erase this properly. Yeah, so sorry. Okay, so now what will happen? So at what does that particular line states is that at minus 270 degree minus 273.15 degrees Celsius or minus 273 degrees Celsius or absolute zero temperature, this particular silicon atom, as you can see, they will form covalent bond. Okay, and they will be present as it is, right? There won't be any change happening in this particular silicon crystal. Okay, I hope you are able to understand this. Okay, great. Now we'll read the further point. Okay, so let me just write over here. There won't be any change, right? Won't be change in Si crystal or Si atom, whatever that is, Si crystal. Okay, so at absolute zero temperature, as all the valence electrons are involved in the covalent bond. Valence means what? The outer electrons, as we had already seen. So these are the 4 valence electrons of this particular silicon atom, and these are the 4 valence electrons of this particular silicon atom, and basically all of these 4 electrons of each and every atom, they are involved in the covalent bond at which temperature? At absolute zero temperature or minus 273 degrees Celsius. Okay, great. Okay, so basically all of them would be involved in the covalent bond. Okay, but now what will happen as I am increasing the temperature? So let's see. On increasing the temperature, more and more thermal energy is available. Some covalent bonds may break. Okay, some covalent bonds may break and some free electrons are generated. Okay, great. So now what is going to happen? Let's see. Okay, so now let's suppose if I am taking the crystal and moving at certain higher temperature, let's suppose at room temperature only, maybe at 25 degrees Celsius. See what we are doing. We were present at minus 273 degrees Celsius, as I had mentioned over here. See, minus 273.15. I'll just take the rough value, that is minus 273 degrees Celsius, and from minus 273 degrees Celsius we are moving to room temperature, that is around 25 degrees Celsius. So you can clearly see the temperature has increased. So as the temperature has increased, that means what? Your thermal energy, or rather you are providing thermal energy to this particular Si crystal, right? So now what is going to happen? See, as soon as we are providing certain energy to this particular SI atom, so what is going to happen? Let's suppose if this is my, let me draw it properly. If this is the energy, if this is the energy that I'm going to provide to this particular crystal, so this covalent bond or the electrons which which were actively participating in the covalent bond, they will come out and they will become or act as a free electrons. Okay, so this electron which was present over here, although I had represented it with the help of dot, okay, but now I am representing it with the help of alphabet E. So you see what is happening. For us, the most important point is to understand the concept. As soon as we are increasing the surrounding temperature, so whatever the electrons that were present in the covalent bond, they will break that particular bond and they will come out of that particular bond. Okay, so long story short, this is what it will happen. Let me just show it to you. Yeah, so this is what we saw in case of at absolute zero temperature, but as soon as the temperature is increased, so maybe this particular bond I will take this time. So this particular bond will get break, and whatever the electron that was present over here, that will jump out and it will come over here, somewhere over here. So now this particular electron, it is completely free to move anywhere. Okay, so this particular electron, it is completely free to move anywhere. Okay, I hope you are able to understand this particular concept. Again, I will repeat, we are moving from absolute zero temperature to room temperature, that is from minus 273 degrees Celsius to 25 degrees Celsius. So during this particular scenario, all of the electrons which were involved in the covalent bond, so they will come out of that particular covalent bond, and now these particular electrons are set or are free to move anywhere. Okay, but not all of them, some of them, sorry, some of the electrons, not all of them. Let's suppose if there are 100 electrons present in the covalent bond. Okay, so out of 100, maybe 2 or 3 electrons will participate over here, or basically 2 or 3 electrons are free to move anywhere. So only 2 or 3 electrons will break this particular bond. Okay, only 2 or 3 electrons will break this particular bond. Okay, rest will prefer to remain as it is over there. Okay, now let's proceed further and let's read the further point. Okay, so the next point states that at this much temperature, that is at 25 degrees Celsius, one covalent bond breaks out of this many atoms. Okay, so practically it is seen that one covalent bond, that means at 25 degrees Celsius, see what does this particular line means. Let me write it properly. At 25 degrees Celsius, one covalent bond, only one covalent bond breaks out of 10 raised to 29 atoms. So basically you assume that there are 10 raised to 29 such atom, right? So there are 10 raised to 29 such atom. So these are 10 raised to 29 atom, and out of this only one covalent bond is breaking. Only one covalent bond is breaking. So this is what this particular line is trying to tell us. Okay, and now if you could remember, I had already mentioned that 1 mole means what? 1 mole of anything, 1 mole of silicon, 1 mole is equivalent to 6 times of, it is generally 6.23, but I'll take 6 times of 10 raised to 23 atoms. So you see, are you able to compare this? So basically we need more than 1 mole of atoms so that this one covalent bond may get break. Okay, because you see this number is quite high as compared to this one. Okay, so you can actually compare these two numbers and you can actually get a good idea of what exactly I'm trying to tell. So only one covalent bond breaks out of 10 raised to 29 atom. It is a huge number, man, 10 raised to 29 atom. So basically if you have let's suppose 2 mole, so out of 2 mole maybe only 2 to 3 covalent bonds will only break. Okay, so over here as well, this is also wrong idea. So basically this is just for understanding purpose, right? 100 electrons, okay, which are participating in covalent bonds, not 100, maybe I have to increase this particular number and keep it as around 10 raised to 29. Yeah, 10 raised to 29. So 10 raised to 29, and over here 1 electron. So 1 electron will get break out of 10 raised to 29 atoms, okay, which are totally involved in the covalent bond. So you can see conductivity is present at room temperature, but it is very less. Why conductivity is present? What is the relationship of conductivity over here? So for that, let's come over here. Just a second. Yeah, just a second. Yeah, you just come over here. Yeah, you see over here at 0 kelvins or minus 273 degrees Celsius, all of the electrons, all of these particular electrons, they were participating in the covalent bond, or rather what I can say, they were present in the valence band. Now why valence band? Valence band. What is valence band? Valence band is a band in which, so long story short, electrons are present in the outermost shell, okay, and as far as conduction band is present, none of the electrons are present in the conduction band, right? So you can clearly see, if I try to plot that particular concept in the energy band diagram, so this is how it will look like. So at minus 273 degrees Celsius or at 0 K, as I had mentioned, all of the electrons, they are taking part in the covalent bond, okay, that means they are present in the valence band condition. But as soon as we increase the temperature maybe to 298 kelvins, that is around 25 degrees Celsius, so now few of the electrons which were present in the valence band, they will start moving to the conduction band. So this is basically my, both of this, they are my conduction band. So you see what exactly is happening over here. So all of these electrons which are available in the conduction band, so because of this particular electrons, there might be certain conductivity, okay, if I provide certain external voltage or anything, so there might be certain conductivity, but that particular conductivity or the current which is generated, it would be negligible or it would be very, very less, okay. So that's the drawback of intrinsic semiconductor. Don't worry, I will elaborate this particular point as we move further in extrinsic semiconductor as well. So I will compare both of this particular intrinsic and extrinsic semiconductor, and then I will actually conclude these particular points. But the point to notice over here is that, see, what I want to convey to you guys is that, see, over here again I just forgot to draw the electron over here. Yeah, you just see at absolute zero temperature, all of the electrons, they are actually participating in the covalent bonds, okay. That means none of the electrons are free, okay. All of the electrons are involved or they are actively participating in the covalent bond, right? So basically I can match this particular situation with the valence band, because you see lots of electrons are available, right? What is the condition of valence band? There are lots of electrons, but they cannot take part in the formation of current, right? So you see over here, there are lots of electrons, but none of the electrons are free, right? None of the electrons can move here and there, because obviously they are participating in the covalent bond, okay, at absolute zero temperature. But as soon as we are increasing the surrounding temperature, so certain electrons get free, and that means, see, again I'll just show over here. As soon as we are increasing the temperature, so this particular electron, it will eject from the covalent bond and it will come out, and then it is completely free to move here and there, right? I hope you are able to understand this particular point, okay. So that means what? That means from that electron, so this particular electron which was present over here, it moved out, right? So basically this particular electron is moving from valence band to the conduction band, okay. This particular electron is moving from the valence band to the conduction band, okay. So now I believe that you understood the concept of intrinsic semiconductor. At least you got a bit of idea of what exactly intrinsic semiconductor is, okay. But still, if you have any doubt, if you are facing any difficulties anywhere, it's my request to you all guys that you please ask me in the communication section, okay. So thank you for listening me patiently. I'm ending this video over here. Thank you.
Bye.